Hello everyone, my name is Liu Han. I'm a senior research scientist at University College Oxford Blockchain Research Center and the founder of Committable as a spin-off from the Oxford Research Center. It's a great pleasure to be part of EDCON this year. So the talk today will be focusing on understanding and incentivizing developers in a collaborative software development process, as we see in many Ethereum and Web3 projects. I will also explain the core protocols and technologies that make this practical and why we believe Committable is going to drive the development of Web3 ecosystem in a truly community-based way. Before I step into any further detail, I would like to start from a case study of OpenZeppelin. I believe a lot of us today are quite familiar with OpenZeppelin as a popular smart contract development library. As an open source project, OpenZeppelin currently has around 400 contributors from all over the world. The development has been relatively active since the year of 2016. If you look at the top 10 developers in the past week in terms of pull request contributions, half of them are actually new names in the list, which indicates an effective growth of its developer community. So the general goal of this case study is a little bit further. We would like to systematically understand the developers' activities, contributions, and more importantly, their relationship. We used a different measurement to evaluate a developer's contribution in the development process, including number of commits and pull requests, lines of code, and our own committable measurement based on structure and semantic analysis, and the dev rank measurement that counts references between functions. We identified the top contributors in the case study and analyzed their rankings across different measurements. The results indicated both consistency and inconsistency on their contributions. More specifically, at least half of the contributors are in all measurements. However, we did see that a top 10 developer with number of commits is not in the list of dev rank. Bots are widely used to submit commits to projects these days. For example, automatic package management, but they are commonly not much related to code level modifications. Moreover, any measurement might introduce bias to developers. Here, the developer is ranked 4 with the number of pull requests, but 198 with lines of code and 147 with committable. That said, the guy was involved in many pull requests, but did not update the project that much. We also analyzed that how much contributions from the project were made by developers and by top developers and other developers. So the general trend of decentralization centralization is pretty obvious in OpenZeppelin. A small number of core developers accounted for the majority of project contributions. Compared to other measurements, Committable and the number of commits are more decentralized in a sense that the share of core developers is relatively less, which indicated that there are non-core developers contributing to new features, bug fixes, and etc., but without many lines of code. So if we look at the developers with a chronological view, we find that many top developers actually joined the project since the very first day. However, some top developers even started since late 2020. So it is never too late to contribute. Some other developers, they quit for a period of time and reconnect later on. For those top developers, it is not the case that they are making the largest contribution all the time. For example, we found that this developer outperformed one of the core developers from the official OpenZeppelin team during 2019 to mid 2022 with the committable measurement. Therefore, the real question to us is, are core developers always more important than others? If not, what would be the solution to the measurement of developer contributions? So to achieve the sustainability of a developer community and make sure all participants are fairly acknowledged, it is critical to not only highlight the top contributors, but understand that every developer matters as well. So our proposal in this context is Verifiable Development Contribution, or VDC. In a collaborative development task, for example, a pull request, VDC is a trusted measurement of development contribution made by all participating developers, and It can be locally verified without a trusted third party. Anyone who sees the VDC is able to understand that which one is making what level of contribution and why it is the case. So the expectations on VDC include number one, it is algorithmic, therefore scales for large projects. It is based on analysis of software structure and semantics. And also VDC needs to be consistent with the priorities specified in a project. And lastly, the verifiability should not require any re-execution of the measurement process. So the value of VDC are twofold. First, it creates a proof of work record, skill set, and project contribution for developers that the community can verify and accept. Also, it is an insight of the development process which helps projects to optimize the software engineering lifecycle and design of project incentives. The idea of VDC goes beyond the individual developer and the project of OpenZeppelin. It actually establishes the connection between projects and developer communities and makes sure that the contributions to a project are reliably rewarded for developers. However, the design of VDC is non-tricky task. We need standard norms to specify priorities in projects. The measurement of VDC should be as not noisy as possible, and it is required to cross different programming languages. We also need to not only deliver the trust for VDC, but also make sure all relevant parties can easily verify. And last but not least, we want VDC to work with multiple contribution measurements rather than a specific implementation. So there are several related projects in the context. For example, GitHub stores important data of developer activities. Gitcoin and Dora Factory provide grant and hackathons for developers. Pope creates proof of attendance in events. SourceCred helps assign contributions in communities. So in general, these projects could make provide fundamental data to refine a VDC. However, when it comes to the measurement of development contribution, existing projects lack development context to generate any in-depth decisions. Yet, we do believe in the potential synergies between VDC and other projects. For example, help enforce a fair distribution of funds or incentives to a developer community. So the core technology to realize verifiable development contribution is trusted software analysis, or TSA. TSA is essentially running software analysis algorithms in trusted computing environments. So the workflow of TSA starts from submitting software artifacts, for example, code, documents, test cases, makefiles, configurations, runtime logs, and many more. TSA then creates a representation for those artifacts. In the case of code, TSA uses abstract syntax tree, control flow graph, or semantic graph to encode the given code. Based on these representations, TSA runs software analyzers to extract fundamental knowledge of a development process. This could be finding data dependencies and function call references, checking access to memory and storage, analyzing the messages and the sanity checks in the code, or it could be collecting statistics of programming structures as well. So the outcome of software analysis comes with a computational proof to certify that the outcome is indeed carried out by algorithms as pre-specified and why it is the case. A TSA verifier can check the validity of the proof to accept the outcome of TSA. In the case of Committable, the trusted computing environment is realized with TEE and zero-knowledge proof, respectively. So we currently support 6 programming languages, including Solidity, Golang, Rust, JavaScript, TypeScript, and Move. We have also implemented several analyzers as highlighted here. In addition to the previous workflow, Committable implements the measurement process in TSA as well, which creates a contribution measurement based on the priority of a development task, the effective workload involved in the development, and the risk introduced to the project. So the proof in this case is either a TE signature or zero-knowledge proof. The implementation with TE is built on AMD SAV. We essentially wrap up everything in a SAV environment and provide the SAV hardware measurement as the proof. We also released the preliminary performance evaluation for TSA with TE. On a public benchmark, TSA introduces an average time overhead of 140% and memory overhead of 50%. So please find the repository on GitHub, the talk, and the paper as well. So the implementation with zero knowledge is a bit different. For example, if we're going to design a Halo 2 protocol for the simple analysis of programming structures, we need to firstly encode the code into, for example, an AST and create a circuit and lookup table to describe the analysis steps. If our goal is to count the number of specific types of AST nodes, the constraints needs to make sure an AST node is valid and the target count value is consistent before and after the analysis of the specific AST node. Obviously, the proof here will be a zero knowledge proof generated by Halo 2. For example, if TSA is working on a DeFi smart contract to generate numeric statistics of software structures, the outcome of the analysis should contain a selection structure because of the required check here, a function called to the liquidate function, 3 states visits on the balance and the message sender variable. More specifically, TSA identifies 2 control flows depending on whether the required passes or not, and 2 data flows from the transaction data to core states and contracts. A contribution measurement is generated then based on the outcome of the analysis and all participating commits of a pull request. So the measurement will be used as a certificate to distribute incentives such as development bounties to developers based on the level of contribution they have made in the pull request. Committable implements the TSA technology and creates a DID protocol for developers. So the vision here is to establish a verifiable link between a developer and any software development process he or she contributes to. These links are building blocks for a community-driven software engineering paradigm where the development of software project is in line with the growth of a contributor. Specifically, the DID is based on a Web3 address and connects to any existing developer account. For example, your GitHub. TSA creates measurement of verifiable development contribution based on pull requests of a project. So the protocol itself defines the commit, COMMIT, commit native NFT as DID profiles to store corresponding measurements generated by TSA. That said, by looking at someone's commit NFTs, we would be able to systematically understand the developer's identity. On one hand, the DID interfaces to collaborative development workflow in the existing ecosystem. On the other hand, the DID is naturally a fundamental information for the developer and therefore can be used in applications such like DAOs, social finance, and many more. So the design of the Committable protocol works as follows. The project owner is allowed to specify a priority, for example, high plus in this case, for a development task to make sure that the participating developers understand that working on this task might yield a higher level of contribution. So the commit record in the project is then analyzed by TSA to generate a piece of metadata to encode the updates on both structure and semantics of the software. A commit NFT is minted out as well and they associate with the developer's DID. When the pull request has been confirmed and merged, the protocol generates a contribution ranking for all participating commits, and the ranking is used in a payroll contract to distribute development incentives to owners of the commits based on their levels of contribution. In addition to only developers, other types of community participants, for example, project sponsors and donors, are potentially recipients of community incentives based on how much they contributed to the most prioritized projects and development tasks. So currently, Committable is running on the Sepolia testnet. Feel free to visit the application through the link here. At this moment, what you can do with Committable includes number one, create your DID while connecting to MetaMask and GitHub. After that, you are able to mint a commit from your project and check it by looking at the metadata it stores and the contribution measurement it is labeled. Your commit automatically goes to any incentive pool it relates to, and you can claim your rewards to your wallet later on. So we're currently running a early bird program on the testnet and plan to release the mainnet version in the third quarter of this year. Any eligible early bird on the testnet will be acknowledged and when the mainnet version is up. So welcome join and try it out. Lastly, I would like to share some of the interesting findings of our developer survey on verifiable development contribution. So the general goal here is to evaluate whether the decisions made by algorithms in Committable are consistent with the opinions of developers. So this is an obvious case where the left commit is considered more contributive than the right. Both Committable and developers understand that the left requires more workload since it sets up the general structure of a smart contract, while the right only fixes several typos. So in the second case, both algorithms and developers pick the left, although the right seems to have more workload. So the reason behind it is that the left is the main commit in a pull request, while the right needs to share the contribution with other commits. Therefore, the right gets favored in this context. The last case indicates the significance of using TSA as the underlying technology for Committable. Although the left commit contains only a single line of modification, it introduces important updates on structure and semantics since this is a gas optimization to make sure the contract rejects any zero-value transaction. The programming and functionality impact are captured by TSA and reflected in the contribution measurement process when it is compared to the right, which adds several event operations to the contract. The lessons learned from the survey are TSA and protocols are fundamental designs to understand the developer context in a more reasonable and unbiased way. Instead of going for a 100% accuracy, we're actually more interested in creating an open and accountable framework where new algorithms can be integrated and everybody can understand the decision-making process of Committable. As we mentioned earlier, Committable will be running early bird programs to onboard developers and projects. We will release the mainnet version in Q3 this year and support for multi-chain deployment. The core TSA framework has been open sourced and will be continuously improved. We welcome anyone who is interested in collaborating with us or building with us to join. Also, it is important to think about the potential CBO attacks. This is going to be very challenging, but we will focus on that as many other projects do. From the technical view, we are working on new designs and optimizations of TSA to make sure it is practically usable in a large scale. Also, we love to hear back from the developers and we'll keep doing case studies with Web3 projects. Hopefully, this will help grow their developer resources in different contexts. So lastly, if you're interested in Committable and the Oxford Research Center, we're around these days at EDCON, we're open to any chat and discussion. Also, welcome take a look at our repository on GitHub, the Twitter account, and the Discord channel. More importantly, go to the application to create your own developer DID. Thank you, everyone.